All right, so now that we've looked at the exponential and logarithmic functions, we want to try to take a derivative. So we're going to start with the derivative of a logarithmic function. All right, so we're going to look at the derivative of the logarithm base a of x. So what I'm going to do is I'm going to write this out as the limit definition, right? This is the limit as h approaches 0 of log base a of x plus h minus the log base a of x over h. Okay, now the first thing that we can do with this thing is we're going to combine those logarithms on the numerator as a single logarithm. This is the limit as h goes to 0 of the logarithm. Actually, what I'm going to write is the 1 over h here. The log. Okay, so I'm going to 1 over h. So pull out that h. This is the logarithm of log base a of x plus h over x, right? And so what I'm going to do is, in fact, I'm going to, so we're going to actually split this inside the parentheses. We're going to split it up into two fractions. So the limit of 1 over h times log base a. So if you split up x over x plus h over x, so it's actually 1 plus h over x. Now we're going. I should mention in the back of our minds we should have this fact that we're looking for. This fact that we're going to try to employ is that. So we're going to use this fact that limit as x goes to 0 of 1 plus x to the power 1 over x is equal to e. So we're going to try to kind of cook this up so that we get it to look like this. And we're not too far off. It's the h's that we're going to be our x, so to speak. So what we want is h over x is going to be this thing. So what I'm going to do is introduce an x to this to get an h over x out front. So I'm going to write this limit as h goes to 0 of x over h and a 1 over x times logarithm base a of 1 plus h over x. Okay, now I'm going to use the fact about logarithms that a coefficient times a logarithm, that we can bring that up in as an exponent. So this is going to be the limit as h goes to 0 of 1 over x times log base a of 1 plus h over x to the power x over, I'll write it as 1 over h over x, right? Just to make it even more clear that that's what we're looking at. Now we're going to use a property of the limits of logarithms, the fact that a logarithm is a continuous function, and we're going to move the limit inside. Okay, so 1 over x has no h's involved, so that could just come out front. Now that's going to stay out front. Then we have the logarithm. Let's do it one step at a time. The limit as x approaches. Okay. Logarithm base a of the limit as h goes to 0 of 1 plus h over x to the power 1 over h over x. Remember, this whole time I'm trying to get this thing to disappear. And now it's exactly in the form I need, because as h goes to 0, h over x is going to go to 0. And so I can actually replace this with just e. So we're going to get 1 over x log base a of e. And that, my friends, is the derivative of a logarithmic function. So let's just state that as a fact now. So the derivative of log base a of x is 1 over x times log base a of e. Now, you can actually use a change of base rule to write this as 1 over x times the natural log of a, because log base a of e is natural log of e over natural log of a, right? And natural log of e is 1. So that's where this derivative comes from. Okay, so putting this into practice, let's find the first derivative of this function log base 10 of 2 plus the sine of x. So we're going to use chain rule. So the logarithm, so the x is the whole 2 plus sine x, so to speak. So the derivative is going to be 1 over 2 plus the sine of x times the natural log of 10. Chain rule says we then have to multiply by the derivative of 2 plus sine x, which is going to be 0 plus the cosine of x. And that's it. That's our derivative. As a special case, the derivative of the natural log, because the base is e, it's just going to be 1 over x, period. That's all there is to it. So the natural log, the derivative is 1 over x. You're probably, if you're thinking about the power rule, thinking like how would we have gotten x to the negative 1? If we just using the power rule, what function would, what power would have x to the negative 1? Well, 0 wouldn't really work, because how could x to the 0 give you x to the negative 1? Well, it turns out the natural log. And if you, well, I won't go into more into that. This is the derivative of the natural log. All right, very cool. So let's just tackle some examples one by one. Okay, so take y equals natural log of x to the third plus 1. A y prime is going to be 1 over x to the third plus 1 times the derivative, which is going to be 3x squared, right? Chain rule. Always remember that chain rule. Okay, so what's the derivative of the natural log of the sine of x? Well, it's going to be the 1 over the sine of x times the derivative of sine of x, which is going to be the cosine of x. And that actually is the cotangent of x. Yeah, that's this cosine over sine. Okay, and let's take the derivative of the square root of natural log of x. So the derivative of the square root, remember, it's 1 over 2 square root of whatever that thing is, which is just natural log of x, times the derivative of that thing, which is it's a 1 over x. So this we could write over 1 over 2x root ln x. So now let's take a look at this. The f of x is natural log of the absolute value of x. So let's take the two cases. So this is going to be it's going to be the natural log of x if x is greater than 0, and it's going to be the natural log of negative x if x is less than 0. So let's take the derivative of the two sides of this thing separately. F prime of x is going to be, it's going to be 1 over x if x is greater than 0, right? And this is going to be the 1 over negative x times negative 1 if x is less than 0. I'm just doing the chain rule just like I did before, but that's actually the same thing. So this is actually 1 over x everywhere. Okay, so now we come to a technique that uses the derivative of logarithms in order to calculate derivatives of complicated functions. It's called logarithmic differentiation. And so if you have a complicated function that involves products and quotients and powers, because logarithms allow you to split up powers and quotients and products and stuff, here's the idea. So let's take this example. I'll talk you through the example, and then we'll kind of write out the steps. So let's take y equals x to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th. All right, and so what I'm going to do is I'm going to use implicit differentiation, and I'm going to first start by taking the natural log of y and setting that equal to the natural log of this thing. And I'm going to use properties of logarithms. I can write this as the natural log of x to the 3/4 plus the natural log of the square root of x squared plus 1 minus the natural log of 3x plus 2 to the 5th. But I'm not going to stop there. I'm going to keep rewriting. So the natural log of x to the 3/4, that's 3/4 times the natural log of x. And this is going to be the natural log, that's going to be 1/2 times the natural log of x squared plus 1. And then this is going to be 5 times the natural log of 3x plus 2. Right? All of those exponential, those powers can come down as coefficients. And now what I do is I take the derivative of both sides implicitly. And so what I'm going to get is 1 over y times y prime. That's going to be the derivative of natural log of y equals the derivative of the right-hand side. That's going to be 3 over 4x. That's for the 3/4 natural log of x, right? Plus we have 1 over 2x squared plus 1 times the derivative of x squared plus 1, which is going to be a 2x. And then we have minus 5 times 1 over 3x plus 2 times the derivative of 3x plus 2, and that's going to be the number 3. And so now to find the derivative, we can just write this as y prime equals this whole right-hand side, 3 over 4x plus 2x. The 2's can cancel, actually. We can write x over x squared plus 1 minus 15 over 3x plus 2. This thing times y. And rather than writing y, the letter y, I'm going to put in the definition of y, which is, I'm just copying it from up above, right? This is just y. So that, I think, is a little bit easier than using the quotient rule with this beast of a function, right? We didn't have to use the product rule. We didn't have to use the quotient rule. So pretty clever, right? Okay, so here's the steps. Here's what I did. First, you take a natural log of both sides of y equals f of x. And then you're going to simplify the right-hand side using properties of logarithms. Okay, next we're going to differentiate implicitly with respect to x, which is, and then at the end we're going to solve the resulting equation for y prime. And actually, if you think about it in general, what you're going to get is y prime is going to be the derivative of the natural log of f of x times f of x. This is like what's going to happen for you when you do this. This is like generally what this is going to come out to be. So this if you remember this formula, you could actually use this. And because if you think about it, right, this whole thing here is just going to be 1 over f of x times f prime of x times f of x, and those cancel, right? So this is just another way of writing out the f prime of x, yeah, using the derivative of the logarithm. Natural logarithm. Now we can use implicit differentiation, or sorry, we can use logarithmic differentiation to prove the power rule for all n. We didn't do that before, but we can do that now. And so f prime of x is going to be the derivative of the natural log of x to the n times x to the n. If you work this out, then you're going to get, this is the derivative of n times the natural log of x times x to the n, and so we're going to get, the derivative is going to be n over x times x to the n. This is going to be n times x to the n minus 1. So this is how you can prove the power rule for any exponent n. It doesn't have to be a positive constant. Using logarithmic differentiation, you can get this for all n. I mean, we already have been using it, but this is the proof, and it's not too bad. Okay, so now let's look at the derivative of the exponential function. So what I'm interested in is finding the derivative of a to the x. So let's write y equals a to the x, and what we'll do is we will find the derivative of this using logarithmic differentiation. Okay, so what I'm going to do is I'm going to take the natural log of y and set that to the natural log of a to the x, right? And so I'm going to actually the right-hand side, I'm going to simplify to be x times the natural log of a, where the natural log of a is just a constant. And so take the derivative of both sides implicitly. What we're going to get is 1 over y times y prime is equal to just the natural log of a. So y prime is going to be the natural log of a times y, which is just the natural log of a times a to the x. So that's the derivative. It's and sometimes people write a to the x times the natural log of a. There's the derivative of the exponential function. Using logarithmic differentiation, it's really easy to get. So that is pretty powerful. This logarithmic differentiation as a technique handles anything with exponents with x's and the exponents and stuff. So as an example, let's just take a look at this one. Let's find the derivative of 10 to the x squared. So this can be found by using this. The base is 10. Actually, you know what we could do? Well, let's do it a couple different ways. One thing we can do is just follow this blindly and just use the chain rule, right? So it's going to be 10 to the x squared times the natural log of the base, the natural log of 10, times the chain rule, which is going to give us a 2x. So that's one way you could handle this thing. Another way you could handle this thing, yeah, I was thinking of something else. Yeah, this is how you would handle it. How would we clean this up a little bit? Well, you could write 2 ln 10 times x times 10 to the x squared. Yeah, I mean, it doesn't clean up really much. Okay, so as a special case then, of course, we have the derivative of e to the x is just going to be e to the x, because the natural log of e is 1. All right, so here's a special one. So now we're going to use this all over the place. For example, y equals e to the tan x. We want to find y prime. Okay, so it's going to be e to the tan x. But the chain rule says we're going to multiply this by the derivative of the tangent of x, which is the secant squared of x. Another little example we'll do. Let's take y equals e to the negative 4x times the sine of 5x. So here we've got to use the product rule because we have this one function times this other function. So y prime is going to be e to the negative 4x prime times the sine of 5x plus e to the negative 4x times the sine of 5x prime. So let's just take these derivatives. We've got e to the derivative of e to any power is that same thing, e to the negative 4x times the derivative of the exponent, which is going to be a negative 4. And then we have the sine of 5x. On the other side, we've got e to the negative 4x times the derivative of the sine function, which is the cosine of 5x, times the derivative of 5x, which is a 5. And that's it. We could clean it up a tiny bit. If we needed to, e to the negative 4x, the sine of 5x, that would be plus 5 e to the negative 4x sine, it's cosine of 5x. You notice that e to the negative 4x ends up being a term, a factor in both of these terms, right? So you could factor that out if need be. In fact, if you're going to be doing a second derivative, it may be prudent to factor out e to the negative 4x, and it might make your life a little bit easier, actually, for the second derivative. Okay, so now let's take a look at this, and using logarithmic differentiation, we could find y prime. We can take the derivative of this, and if you wanted to use the formula that I gave a little bit ago, it would save a little bit of time. Y prime is going to be, remember, it's going to be the derivative of the natural log of x to the square root of x times y. But let's just use logarithmic differentiation. Let's use logarithmic differentiation. So we're going to take the natural log of y, set that equal to the natural log of x to the square root of x. And I'm going to write the natural log of y equals root x times the natural log of x. So on the left-hand side, we'll have 1 over y times y prime. On the other side, we're going to get this. We're going to have product rule. So we're going to have 1 over 2 root x times the natural log of x plus square root of x times 1 over x. And we're going to, y prime is going to be, I'm going to have to multiply by y, and that's going to be ln x over 2 root x plus 1 over root x. That's what I get when I divide square root of x by x. And so we are going to get, we can then replace the y with x to the root x. So y prime is going to be x to the root x times, do I want to put these together? I kind of want to. I could multiply this by 2 over 2. And so I could write ln x plus 2 over 2 root x. That's kind of satisfying for me. Yeah, so we've got these derivative rules now we can use for exponential functions, for logarithmic functions, and the technique of logarithmic differentiation. Very handy, very useful. And that is it for now. Okay, so get some practice, work this stuff, and you'll become an